All right, don't know how much was missed, but let's see, there's all the work right there. And then we ended up with that number of joules, converted it to regular calories, and then into food calories. The laws of thermodynamics. One of them, I consider a very depressing law, but we'll get there. So let us start out with, of course, the 0th law of thermodynamics. Not the first law, but the 0th law. If system A is in thermal equilibrium with system B and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. I know, it's earth-shattering. If these two things are equal, if A and B are equal, and B and C are equal, then A must be equal to C. Let's hit a couple of vocab words here. Well, actually, let's give people a chance to write it down and then talk through the vocab. In math class, you might have been called the transitive property of equality. I don't know if that terminology means anything. Okay, good. At least to one of you. All right, what does thermal equilibrium mean? And I open this up to the class. Just take a shot. If you're wrong, you're wrong. It's okay.
Same temperature?
Say it again.
Same temperature?
Yeah, pretty much. That's probably the shortest version of it. It doesn't mean that there's not an exchange between it. If I've got these two systems next to each other, yeah, they're pretty much the same temperature, but there might be some fluctuations on both sides. It's close enough to the same that the physicist going, yeah, good enough. All right, so if I have a classic mercury thermometer or whatever they use nowadays, alcohol, what's in thermometers now? Doesn't go with what I grew up with, mercury thermometers. If I have a mercury thermometer, and of course, mercury is enclosed in glass. If this were a thermometer measuring the temperature, measuring for the room, the question is, what is the temperature that the thermometer is measuring? How much heat? Heat, from a physics point of view, heat is energy that's exchanged with something else because of temperature differences. A thermometer on the wall for the room, and it reads some temperature. It reads something which we would translate as a temperature. What is it? It's measuring the temperature of what?
Air.
Pardon?
The air.
You said the air? Not really.
The mercury in the thing?
Yes, that's what it measures. But we assume that the room is in thermal equilibrium with the glass, and we assume that the glass is in thermal equilibrium with the mercury. And if that's the case, by the zeroth law of thermodynamics, this also must be the same temperature as the room. But we are making that assumption. It's similar in my mind that if you stand on the scale, it's really measuring normal force, but if I'm in equilibrium, then the normal force is equal to my weight. So if I'm in thermal equilibrium, the temperature of the mercury would be the same temperature as the glass, which would be the same temperature as the room, or air in the room, more specifically. Zeroth law. Potentially not earth-shattering yet. First law of thermodynamics. Why would they bother coming up with the zeroth law? Why didn't they just make this the first law? Reach into your head about why you on earth would you have a zeroth law instead of just making it the first.
Because you made the first one first?
Yes, pretty much. They figured this one out. They realized this was more fundamental, but it was realized after the other one. All right, so first law of thermodynamics. This is another one that is, did they really need to come up with a law for it? But they did. They felt it, they did. First law of thermodynamics. I've actually already done it. I have energy that I put into a system that starts out with a certain amount of initial amount of energy. It will end up with a certain amount of final amount of energy, and it will lose a certain amount of energy. First law of thermodynamics is just conservation of energy. That if I take what I start with, plus what I put in, I end up with whatever I have, plus how much I got rid of. Again, not particularly earth-shattering. Let's see. I had the fancier version of it. It's generally, this is the essence of it. Thermodynamics is more likely to write Q equals delta E plus W or minus W, depending upon the system that they're using. Because if I stick with letters that we already know, when we can throw a few extra ones in. All right, first law of thermodynamics. So first, zeroth law, transitive property of thermal equilibrium. Second law, conservation of energy. Second law, this is the depressing one. There is, should be a link to the video under, I might have put it under videos to watch, or it's going to at least be in the supplemental material videos on it, put out by a YouTuber who goes by Melody Sheep, and probably the best demonstration of the second law about sort of the implications of it. There are several different variations of a theme here. Let's just say, in the end, the universe is filled with elementary particles all with the same energy. Doesn't necessarily seem depressing on the surface of it, but it's the fact that eventually our bodies will decay, we will become potentially ashes to ashes or dirt to dirt, but eventually the earth will disintegrate, the sun will end up not existing. Everything is going to break down into elementary particles that are then floating through whatever's left of the universe. All right. This also has a different variation of it, is that entropy increases entropy is it's a label that's put onto sort of the order that everything is in. Right now, everything's in a particular place right now. If I were to change that, it will take energy to do that. So I drop a marker onto the floor, I use a certain amount of energy to do that, which would have, a small little burn of calories. I now lean over, I pick it up. I am giving this pen energy because I've increased its potential energy. But in order to do that, I had to use some of my own energy. And as a matter of fact, the amount of energy I put into lifting it was more than it gained. So, if I want to change the order of things into a different configuration, if I want to put the marker on the table, it's going to take more energy to do that than I gain by actually doing it. So we can write this. So entropy is, I forget how I just defined it. It's sort of it's a number associated with the way things are. It will increase as things become more disordered. Another way of reading the second law of thermodynamics is, in reality, there is always energy loss. Statistically speaking. Up in the Bat Creek area of South Carolina, they've got, in the 90s, they built a huge reservoir that they pump water up into it, and when they need a quick boost of energy, they basically drain this mini lake, dump it into, Lake Jocassee? What is the lake up near Clemson? Anyone know? Okay, whatever it is. Actually, Bat Creek is just over the South Carolina line into North Carolina. But they basically fill this reservoir up when they have enough energy to do it. They'll basically pump water from whatever lake that is up into the reservoir. And then during peak energy use, they will quickly drain it. They'll run the water back down into the lake, creating energy. Now, the amount of energy it takes to get the water into the reservoir is more energy than they will get when they drain it. Second law of thermodynamics. It's just a matter of when they have extra energy, they put it into the reservoir. When they need it, they take it out. And so it's a matter of distribution of it. But in the end, it's a loss of energy. But But they don't mind because we pay for it. Want that? Want that? All right. The final law then, of which I know maybe someone's coming out with a fourth one since I last looked. The third law of thermodynamics. We've talked about absolute zero. We talked about the fact that temperature is related to the average kinetic energy, and they're all alternate definitions of it. But if I have a gas here at a certain temperature, I have some sense of what the average kinetic energy is. If I start cooling it down, the particles inside will not move as fast, and eventually, if I can get it, in theory, get it down to the point where they stop moving completely, I'm at absolute zero. Third law of thermodynamics says it is impossible to reach absolute zero. Because frankly, I could slow an object down more and more, but how do I actually know how fast it's moving? Well, I have to basically bombard it with something in order to know you have some sense of how fast it is. And by measuring it, I'm altering it, it won't be at zero anymore. So I guess you could get down to absolute zero, but you would never know it. But how close have they come? And I know I've got these written down somewhere. It's part of what I was looking for. There we go. At least as of this writing. There was, in 2000, a group got it down to, remember absolute zero is 0 Kelvin. There was a group in 2000 that got to 100 picokelvin. That's 10 to the negative 10th Kelvin. And there's another, so that's the lowest anyone has gotten. There's another group that has gotten the gas down to, sodium gas down to 5 times that, and then the coldest molecule was 2.5 times 10 to the negative 3rd Kelvin. So let me ask you, why do they do it? Why would someone spend time trying to hit absolute zero when, according to the literature, you're never hitting it? Would it help in terms of motivation to say that most physicists are men? What would be the motivation for doing it? Yeah, pretty much. I was about to say to impress women, but no. Bragging rights. There's some nobler thought sometimes that it's actually done just to test a theory, but I'm not buying that as the primary motivation. All right, any questions as we do an awkward transition to new material? Alright, so today is the 14th. So it's 14, tomorrow's 15, that's lab. That was in 13 there, so then 20, 21, 22. So let's say master set for 15 through 18, do a week from today. The 21st.
And then the homework is due the 26th.
Oh, the chapter 11 through 14? Yeah, before Thanksgiving, which puts it at the 26th, yeah. Sorry, that's it, so 20. Is that the 27th?
26, I think, is the ones that we don't have.
This one's wrong.
That,
It's 26th.
This one does not.
oh, that could be a 12 there, 19. That's 26, okay, there we go. And so the 26th,
Is it Tuesday?
it's the 11 through 14 is due. Yes?
When's the next exam?
Oh, talk about that.
Are we gonna have
Because-
a quiz on chapters 15 to 18?
15 through 18?
I mean, 15 to 18.
Okay, so you got that multiple choice test that you did the first day.